Okay, Unit 5, Lesson 6, everyone's favorite. We are proving that an equation is an identity using your understanding of other trig identities, already developed trig identities. So I briefly touched on this in the last lesson, but just wanted to again, look at the difference, like how do we know if an equation is an identity? What is the difference between an equation and an identity? So an identity is an algebraic statement that is true for all values of the variable. And when I say the variable, we mean the independent variable. No matter what independent variable we put in, we will get the same value back out every time. And so, for example, if we have 3x plus 2 equals 5, this is an equation. Now, we could solve this. We could subtract 2 on each side, divide by 3, and figure out that a solution to that equation is x is equal to 1, and that is the only solution that will make the left side of this equal the right side. So this is an equation with a solution. This is an identity. 3x plus 2x is equal to 5x. No matter what we sub in for x, 3x plus 2x is always going to be equal to 5x. Now this is like a really simple example, and when you see this you're probably like, why are those not combined? Why doesn't it just say 5x equals 5x? But just to show you that two things can be equivalent but not expressed in the same way. They could look different. We've already experienced this a ton in this unit. And so this on the left is an equation, only true when x is equal to 1. On the right, this is an identity. It's always true for all values of x. So we are trying to determine throughout this lesson whether certain equations are in fact an identity, or trying to prove. It is suggested that they are an identity, but we need to prove that what is on the left is in fact the same as what is on the right. And the best way that we could do that, like if this was the case, if I said prove that this is an identity, well, it would be so simple. We would just say, okay, well, 3x plus 2x is 5x, and that's what's on the left side, and the right side already had 5x, so therefore it's an identity. Obviously, it's not going to be that easy for us, but essentially that's what we're doing. We're trying to simplify one side to make it look the exact same as the other side, so that we can say that they are equivalent, and that no matter what we sub in for x, what is on the left is going to equal what is on the right. So we already know lots of identities, and you guys have your kind of identity cheat sheet that you're working with, and so we went through this in the last lesson, so I'm not going to go through it again, but you guys have had this. You have a copy. Hopefully you've printed it out if you have the means for that, but any of these identities are fair game as we go through these last two lessons, and we do need to be able to apply these as well as our compound angle formulas, double angle formulas. Now I will say that today's lesson, lesson 6, primarily focuses on review from grade 11, and so we will be using our Pythagorean identities, our quotient identities, and our reciprocal identities primarily today. Those are all ones that you already knew from grade 11. And then as we get into some trickier identity proofs in lesson 7 is where we're going to start introducing our correlated angles, double angles, compound angles, and so on and so forth. All right, so I think what I'm going to do for this lesson, actually first let's just go through some tips for dealing with identities. So number 1, handle the left side and the right side separately. So we are never trying to move things, and so to give you an example of that, we saw in the last one, or in the example, it was 3x plus 2x equals 5. So 3x plus 2x equals 5x. Now again, this is super simple. What we are not trying to do here is move something that's on the left over to the right to then say, yeah, 3x is equal to 3x. We're not moving things over when we are proving identities. We are trying to prove that as it is, what is on the left is equal to what is on the right. And so we keep everything on the left, we keep everything on the right, and we handle them separately. Sometimes we only have to simplify one side, and sometimes we have to simplify both, but oftentimes it's only one. And so with that, another tip may be to begin with the more complicated side. Often we're trying to take something that is very complicated and simplify it in a way so that it looks like the more simple side. So like, again, this is not complicated, but we're obviously going to do something with this to try to make it look like this. We're not trying to manipulate the 5x to look like this. So begin with the more complicated side. If possible, change everything into sine or cosine. Most of our identities are written in terms of sine and cosine or tan, but sine and cosine are much easier to deal with. We are much more comfortable. We have more identities for sine and cos, so wherever possible, we should be rewriting things as sine and cosine. Remember your algebra rules when rearranging. Like, that's more so not rearranging like solving algebra, but rearranging expressions in terms of order, making sure that the sign in front of a term stays with the term, or distributing if there's like a negative outside of a bracket, making sure we're distributing it in, and things like that. Replace existing identities with simpler ones where possible. So again, we're trying to make this as easy as possible for ourselves. Common denominators are often necessary if you are dealing with the sum of any two rational things. Don't forget you need a common denominator to combine them. So that's it. Those are just some 5 tips and tricks, but really important. Keep what's on the left, what's on the right. Change everything to sine or cos. Be careful with your algebra, and continue to replace existing identities with easier ones. Okay, so now what I'm going to recommend, these are all, like I said, essentially things that you may have already done or should have been able to do in grade 11. There is some factoring that goes on as well, and we did look at, when we solved trig, quadratic trig equations, we did look at how we can factor some of these expressions and using the same factoring methods that we use for polynomials. So I think what I would like you guys to do, I mean, best case is you pause the video right now. I did post a picture of these identities, and my goal was that you work through them independently and then use this video as a way to check your work, especially given that this is review from grade 11. The thing with identities is, like, it's trial and error. And you only get better by doing it. There is no steps to follow. There's no formula. There's some tips and tricks, but other than that, it's just putting in the time and kind of staying with it. And maybe it's like kind of like doing one of those mazes. You like, oh, I think I got to go this way, and then you reach a dead end. You're like, what the heck? And you got to go all the way back. And that's trig identities. And so, yeah, have fun with it, play with it. Struggle with it, come back, check your work. If you're like, I don't even know what you're talking about, what do you want me to do with this? Then stick around, watch the first example, we'll do it together. And then beyond that, again, ideally you go and you start attempting some of these on your own and using this video to check your work. All right, so if you're sticking around for the first one, let's go. If you're not, hasta la vista. All right, so let's look at some identities. We would like to prove that this is true. In other words, we want to prove that what we see on the left side is equal to the right side. So again, we're going to start with the side that is more complicated. We're not going to take this tan squared theta and start pulling it apart trying to make it look like this. We want to take this and simplify it to make it look like this. So how can we do this? Well, there's a couple things going on here. Remember that we said we always want to write things in terms of sine and cos if possible. Actually, this one's kind of interesting because we kind of go against that. But okay, let's do this. Let's go on the right side. We have sine squared theta. And why don't we say that that is equivalent to sine squared theta over cos squared theta. So best case is that we get whatever is over here on the left to look just like this on the right. Now, I am seeing 1 minus sine squared theta, and what I know based on my Pythagorean identity is that sine squared theta plus cos squared theta is equal to 1. So if I subtract sine squared theta from both sides, I get cos squared theta is equal to 1 minus sine squared theta. So I can rewrite this first fraction as 1 over cos squared theta and multiply that by sine squared theta, which is sine squared theta over 1. And when I multiply top and bottom, I get sine squared theta over cos squared theta. Easy peasy. Left side equals right side. Therefore, it is an identity, meaning for all values of theta, this is equivalent to this. Okay, so if you wanted to just stick, that was very easy, but that's essentially what we're trying to do here, manipulate one side to make it look like the other, following algebra and trig identities. So if you're just returning back and you're checking your work, let's keep moving. Prove that the following is an identity. So cos x times tan x divided by sine x is all equal to 1. So what we're going to do here, well, there's a couple ways we could do this. If we multiply fractions straight across, we multiply the numerators, if we multiply fractions, we multiply straight across. So we multiply the numerators, we multiply the denominators. So we could also say this is the same as, there's a few ways we could write this. This is the same as cos x times tan x divided by sine x. We might write it like that. That's fine. We could say that this is cos x times, instead of tan x, times sine x divided by cos x, because tan x is sine x over cos x. And technically, it would be all of this, but order of operations is going to force us to multiply these and then divide. So it's all of that divided by sine x, but we could rewrite that as multiply by 1 over sine x. So when we multiply cos x over 1 by sine x over cos x, those cancel each other out, or essentially they become 1s. And so we're left with 1 times sine x, which is sine x, over 1 times 1, which is just 1, multiplied by 1 over sine x. And notice that these are reciprocals of one another. Sine x over 1 and 1 over sine x are reciprocals, and what we know about reciprocals is that they should always have a product of 1. But again, when we multiply these, we could go one step further and say that this is sine x over sine x, and anything divided by itself is just equal to 1, and that was our left side. And on the right side we already had 1, so therefore left side equals right side. Yes, an identity. Okay, so that was example 2. Example 3. Prove the following identity: sine theta divided by tan theta is equal to cos theta. So similarly, I'm going to rewrite this as sine theta over 1 divided by tan theta, but I'm going to rewrite tan theta as divided by sine theta over cos theta. This is my left side, and on the right side I have cos theta. So sine theta over 1 I can say is times cos theta over sine. So we keep the first fraction, change it to multiplication, flip the second fraction, times sine theta. And again, we have that cross-canceling that can happen. That cancels out with that. And we're just left with 1 times cos theta over 1 times 1, which is just cos theta. And on the right, we have cos theta. So we could say, therefore, we could say left side equals right side. Therefore, yes, this is an identity. And tip is all of them are identities. So we should be able to prove all the ones that I've provided to you in this lesson. I wasn't cruel. I didn't give you one that wasn't an identity to let you sit and struggle with it. Okay, so prove the following identity. Cos is equal to 1 over cos minus sine theta times tan theta. So remember that we're not always just trying to manipulate the left side. We're trying to manipulate the side that is more difficult. So we're likely just going to leave this left side as cos theta. And on the right hand side, we got to start playing around. So we have 1 minus cos theta, 1 over cos theta minus sine theta times tan theta, which is sine theta over cos theta. So I can simplify this and say 1 over cos theta minus, on the top, this would be like sine theta over 1 multiplied by sine theta over cos theta. So we would multiply our numerators, which would give us sine squared theta over cos theta. And then we could simplify these. Now we have two fractions and they already have a common denominator, which is beautiful. So we could say 1 minus sine squared theta over cos theta. And we are trying to make this look like cos theta all by itself in the numerator. There is no denominator over here. So like we know we need to get rid of this cos theta in the denominator. Likely how we're going to have that happen is by canceling it out with the cos theta in the numerator. So we're looking at this numerator and thinking, how could we rewrite 1 minus sine squared theta using cos? And that is our Pythagorean identity. And so cos squared theta is equivalent to 1 minus sine squared theta over cos theta. And at this point, I would understand what you did if you just crossed out this and then wrote as cos theta. However, just to show some people why we can do that, cos squared theta, that's equivalent to cos theta squared. So we could rewrite this as cos theta times cos theta all over cos theta. And those are both factors. We can cancel them out, and we are just left with cos theta. So the left side is equal to the right side, and therefore, yes, this is an identity. Okay, it's kind of fun, isn't it? It's like a little bit of a puzzle. Just wait till we get to lesson 7. So we have worked through 1, 2, 3, 4, 5, 6, 7, 8. Is there 8? 1, 2. I thought there was only 7. I think I only included 7. I missed one somewhere on here. Oh well. All right. 1 minus, oh, this one's fun. 1 plus sine x times 1 minus sine x is equal to cos squared x. So, when I look at this, I see essentially, let's write this out, 1 plus the function. I'm going to write it as like 1 plus x and 1 minus x. And when we have factors like that, what's jumping out to me, when we have something plus something multiplied by that same first something minus the same second something, I'm seeing difference of squares. So right away I'm like, oh, this must have been a situation where we had 1 squared minus, it would have to be different, 1 squared minus sine squared x, because this is the square root of the first plus the square root of the second multiplied by the square root of the first minus the square root of the second. So I can rewrite what is on this left side in this way, but what we know is that 1 squared is just 1. So this is just 1 minus sine squared x, and what we know about 1 minus sine squared x using our Pythagorean identity is that it is equivalent to cos squared x, and so left side is equal to the right side, therefore identity. It is an identity. Okay, so we have, I guess, 3 more. All right, so prove the following identities. Sine squared theta over 1 minus cos theta is equal to 1 plus cos theta. All right, so there's a few things we can do here. I'm seeing that sine squared theta, and to me, as soon as I see that, I'm thinking the Pythagorean identity. So, and I know that there's already lots of coses involved here. So let's convert this using our Pythagorean identity. So we're going to take a look at what's on the left. We're going to replace the numerator with 1 minus cos squared theta, that is equal to sine squared theta, divided by 1 minus cos theta. And note that this, I cannot just cancel out one of these. That is not allowed. It has to be a factor, meaning it would have to be something that can be factored out of both terms, So that's what's on the left, and on the right side, I have 1 plus cos theta. So, what I can do is rewrite that numerator using a difference of squares. 1 is a perfect square. I can take the square root of 1 and it's just 1. And cos squared theta is a perfect square. I can take the square root of that and just have cos. So I can rewrite the numerator as 1 plus cos theta times 1 minus cos theta, all divided by 1 minus cos theta. And now this is a factor, top and bottom, the entire thing. If I factor that out, I would be left with 1. Technically, this times 1 is equivalent to just this. And so those can factor out, and then what I'm left with is 1 plus cos theta, which is what we already had over here, left side equals right side, therefore identity proven. I don't really care about the therefore statements so much in these, but just recognizing that that's how we prove that it's true, is by showing that the left side is equal to the right side. Okay, we have two more. This one, I thought this was the last one. Okay, so that's why. So I missed this one on here. All right. All right, so sine squared x minus 7 sine x plus 10. So this is where we have that quadratic trig function in the numerator, actually, and the denominator. And this one is actually very, very easy, so don't let it scare you. But again, if you wanted off to the side, aside, you could say let x equals sine x. If you wanted, you could rewrite this then as x squared minus 7x plus 10 over x squared minus 25. So you could do it like that. And then this becomes a very simple trinomial that we can factor. So two numbers that add to negative 7 but multiply to positive 10 would be negative 5 and negative 2. And then this is a difference of squares as well. So we have x minus 5 and x minus, I'm just rewriting the numerator, and x plus 5. And we could even do some canceling while it's still been substituted. But at this point, we're left with x minus 2 and x plus 5, and we said that x is sine x. So we have sine x minus 2 left in the top, and sine x plus 5 left in the bottom, and that is exactly what we had on the right side. So therefore, identity is proven. Okay, left side equals right side, therefore identity. So we have one last one, and I know these ones are pretty easy, but we gotta kind of just get warmed up for what's to come in lesson 7 and build some confidence and recall some of the processes and the tips and tricks and whatnot. All right, so this one is a little bit trickier, and we are kind of getting more towards a grade 12 level identity at this point. So, all right, obviously what's on the left looks like it is a little more complicated than what's on the right. So let's play with what's on the left. 1 minus secant squared theta. So again, I'm seeing that difference of squares. So let's rewrite this as 1 plus secant theta times 1 minus secant theta. Now, anytime we can, we should rewrite our functions using sine or cos. So we could say 1 plus secant is the inverse of cos. So we could say 1 plus 1 over cos theta times 1 minus 1 over cos theta. We need to clean this up, so we need a common denominator. So we could rewrite this as cos theta over cos theta, because that's just 1, plus 1 over cos theta. And again, cos theta over cos theta minus 1 over cos theta. So now we can simplify what is here. We have cos theta over cos theta plus 1 over cos theta. So altogether we have cos theta plus 1 cos thetas. So cos theta plus 1 over cos theta. And over here we have cos theta minus 1 over cos theta. Okay. My ears are killing me from wearing these headphones, so I've been doing a lot of recording. All right, cos theta plus 1 times cos theta minus 1. We're multiplying fractions here, so we just multiply straight across. So let's just leave those as cos theta plus 1 and cos theta minus 1 all over cos squared theta when we multiply our denominators. Okay. Oh, I know what we can do. So this, again, we can reverse that difference of squares. So this is cos theta plus 1, cos theta minus 1. So let's rewrite this as cos squared theta minus 1 over cos squared theta. Now that, again, we can't cancel those out. That is not helpful for us. And this is not our trig identity for Pythagorean. So, and the reason I say that is we know ultimately we're trying to get to tan squared theta, and we also, right from the hop, probably should have and could have gone over here and said that this right side is equivalent to negative sine squared theta over cos squared theta. So we should always rewrite them if we can, and over here is what we're dealing with on the left. So I'm thinking I want sine squared theta in the numerator, but if we're dealing with our Pythagorean identity, just kind of off to the side here, sine squared theta is equal to 1 minus cos squared theta, right? So when we subtract cos theta from both sides, but that's not what this says. So I would like it if it said that. So what I'm going to do is factor out a negative, which is great because I need a negative out in front anyway. And when I factor out a negative, I'm left with negative cos squared theta plus 1. And this is a lot of, like, I'm writing out every little step just so you guys can see what's happened. I could then rewrite that numerator. I could reverse those and say that it is the same as positive 1 minus cos squared theta all over cos squared theta. And now I can use my Pythagorean identity. 1 minus cos squared theta is sine squared theta. So finally I could say negative sine squared theta over cos squared theta, which is exactly what we had over here on the right, negative sine squared theta over cos squared theta. So left side equals right side, therefore the identity is proven. Okay, so that's fun. Practice. Page 417, number 3. So it's asking, it's giving you two different things and asking you to graph them. So it would be like giving you this and saying graph this and then graph this and prove that they are in fact actually equal to one another. And so you get to kind of play around with the graphs first, because again, it's kind of nice, that visual, to see like, oh, this that's on the left really is the same as what's on the right. And so you'll just graph using tech, and then in number 4, it's asking you to actually prove those identities using similar methods that we learned in class today. Number 5 is like a question that asks you for like what do we call, like an argument against, or like an anti-example, like to show why the examples in number 5 are not identities, so an argument against essentially. Number 8, you're just proving some identities, and then there's some more challenging ones if you're like, yeah, this is a joke, I got this. Give number 9 a try, and that would be more similar to some of the ones that we will see in our last and final lesson for this unit. So lesson 7 is our final one coming up. Okay, have some fun with it.